Hi, welcome to our first video for 6.7 Geometric Series. This is our last lesson for this chapter. So far, recently in this chapter, we've learned arithmetic series. Well, let's start with the sequence first. So arithmetic sequence, this is when our terms go up by a constant difference or a common difference. So in this case, it would be plus 4 to go to each term. So we would say our first term is 1, our common difference is 4. And to write this as an explicit formula, we would say Tn equals the first term plus the common difference times n minus 1. Okay, if we wanted to add up all these numbers in the sequence, we would then call it an arithmetic series. So the arithmetic series formula is just a little bit slightly different. Okay, to do that, so to find the series, to find the sum of all the terms, we take the number of terms and we divide it by 2, and then we add the first and last term together. And we multiply it by half the number of terms. So again, this is the first term, this would be the last term. If we don't know the last term, well, then we might do is we might take this explicit formula and substitute it in there, and then rearrange the equation to get the second one, n over 2, and then it's 2a plus d times n minus 1. So both these equations work well for finding the sum of those terms. So what we're going to do today is we're not going to be working with arithmetic series or sequences. We're going to be working with geometric. So if you remember geometric sequence, so this will be most important for today. Okay, the geometric sequence usually follows a pattern like 1, 2, 4, 8, 16. And this is pretty obvious. We're just multiplying by 2 each time. So this one doesn't have a common difference. It has a common ratio. So that ratio for R would be 2. And our explicit formula could be written as T of n equals A times that common ratio to the exponent n minus 1. So now, how do we add up all these terms in the sequence together if we're looking for the total? That's what we're going to focus on doing today. So the chapter opens up talking about the Canadian Open. Okay, this is an outdoor tennis tournament. The tournament started in 1881, so tennis is an old sport. And the men's and women's events alternate between Toronto and Montreal every other year. And the first round of the men's singles event, 32 matches are played. In the second round, 16 matches are played, and so on. These numbers form a geometric sequence. To determine the total number of matches played in this event, you would need to add these terms together. When the terms of the geometric sequence are added together, the result is called the geometric series. So whenever you see the word series, whether it's geometric or arithmetic, we're talking about the sum of all the terms in the sequence. Okay, so let's begin here with our formula. So the formula is a little bit complicated. It's a little more complicated than the arithmetic one, but it's so easy to use. So the series is equal to A is our first term in the sequence, and then we have the common ratio raised to the exponent n, and then we subtract 1 from that. Okay, so 1's not, be careful, this is not in the exponent, okay, like it is up here. And this series, it's r to the exponent n, and that power, and then we have subtract 1 after. And then this is all over r minus 1. Okay, so R is the common ratio. Okay, if you ever need to find the common ratio and you're not sure, just take a term and divide it by its previous term. That's the best way to find the common ratio. And then obviously A is the first term, and then N represents the number of terms. Okay, so instead of just going ahead and using this formula, we're going to do a proof first. So it says when the terms of a geometric sequence are added together, the resulting expression is called the geometric series. The sum Sn of the first n terms of a geometric series is. So we're going to start, we're going to write out the series. I think that's the easiest way to do it, kind of like what we did yesterday. So we'll say the series is equal to, our first term is A. The second one, because it's a geometric sequence, we multiply it by R to get the next term, the common ratio. So we'd have A R squared for the next term, and then we multiply by R again, and we'll get AR cubed. You guys get the idea. This goes all the way until we get to our last term, and that means we would have multiplied by Rn minus 1 times. Okay, so this is the whole series. And we have a total of n terms here. So then it says multiply both sides by R and align the like terms. So now we're going to multiply everything by R. So multiply the left side by R, so we have R times Sn. Then it's going to equal AR. So when I multiply this by R, I don't want to write it here. I want to actually move it over here. So we're going to have A times R. Okay, that one goes here because we want to line these up. Okay, the next second term, when I multiply that by R, I'm going to end up getting AR squared. And you guys get the idea. So this is going to keep going on, and then I'm going to have the term just before this one here would actually be ARN minus 2. If I multiply this by R to the 1, we have the same base. So we'll be adding the exponents together. So the n minus 2 plus 1 would end up becoming n minus 1. So the term right there is going to become AR to the n minus 1. And then this term right here, multiply that by R, and we're going to have A times R to the n. Okay, just to show you, to make sure you understand that, if I multiply this by R, this is to the exponent 1. So when I multiply those, I'm going to get A. A is like the coefficient. And then this power times this power, I have to add the exponents together. So n minus 1 plus 1, the ones cancel out, and I just get AR to the n. Sorry, I didn't write the R there. It would be R n minus 1 plus 1, and the ones cancel. So that's how we get this here. Anyway, this is just the proof. So we were just kind of lining things up. So if you notice, all of these line up exactly. You don't see this one, but they all line up in the right column. Okay, and the only one that's sticking out is this one and this one. Okay, so now it says subtract equation 1 from equation 2. So this is 1, this one is 2. So we want to do 2 minus 1. So we want to do this one minus that one. So we would have, I'm kind of going to switch over to green. So this would be like if we were doing the subtraction of 2 minus 1. So I'd have RSN minus SN, and that's going to equal. Now notice I have this equation. It's basically this whole thing minus this whole thing. So this minus this gets canceled, this minus this gets canceled, and everything in between gets canceled with that. This gets canceled with this. So I'm really left with this here, and a negative one of those. So if you think about it, there's like a 0 here. We'd have 0 minus a. So we're going to have negative a. And then we have this term that's by itself minus 0. So it's going to be plus ar to the n. All right, now it says isolate for Sn in the equation. So to do that, I'm going to factor out an Sn. So I'd have Sn times r minus 1, and that's going to equal a. I'm going to factor out a on this side also. So we would have negative 1 plus r to the n. Okay, now we're going to divide both sides by r minus 1. That cancels with that. In my last line, I would have Sn equals a, the a right here. And then this bracket, I'm just going to rearrange this so that it's r of n first. So it'll say r to the n minus 1. And then that'll be over r minus 1. So there you have it. That's the derivation for this geometric series. So it's derived in a similar way to the arithmetic series where we write out the sequences and then try to isolate for Sn by working with those equations that are there. Like I said previously in the last lesson, you don't have to do this on the text. It's just kind of nice to see where these equations might come from. So hopefully you're able to follow along with this. I don't expect you to do something of this capacity on your own, but hopefully following along with the steps, you're able to kind of see how we derive that. If you need another look at it, you could also find this on the textbook on page 403 if you need to see it again. All right, so let's go on to our first example. So this is kind of more important, what we need to be able to do from this lesson. So we want to be able to solve the series. So this first example says determine if each series is geometric and then justify your answer. So we actually don't even want to find the series here. We just want to know if it's geometric. So we have 2, 6, 18, 54. So the question we need to ask, is there a common ratio? Okay, if there is, then we can say, yes, it's geometric. If not, then we'll have to say it's something else. So to do that, we should check the ratio between consecutive terms. So r is going to equal like t2 over t1. Okay, so divide this by this. That will give me the common ratio. So 6 over 2, and I get 3. So that's it for the first two terms. I can check within term 3 and term 2. So we'll divide this one by this one. So t3 over t2. It's going to be 18 over 6, also 3. And our last one, 54 over 18. That also looks like that's 3 as well. So because there is the common ratio between all of the terms, it is therefore geometric. So we can say since the common ratio is 3, the series is geometric. Okay, now the second one, do we still have that common ratio? So let's try t2 over t1. 8 over 2, we get 4. Okay, let's try the next two. So we'd have negative 12 over 8. That's definitely not 4. That's negative 1.5. So therefore, we already know it's not geometric. Let's just try one more. 16 over negative 12. That's 8 over 6, which is about 1.3 repeated. So that'll also be negative. Okay, so You could say since there is no common ratio, the series isn't geometric. Okay, so that is it for this first video for this lesson. I'll see you in the next video.